A powerful X-ray instrument was waiting for a scientist to align a crystal. 6 motors controlled the sample and detector. The crystal's orientation was unknown, the useful diffraction peaks were difficult to locate, and even a small positioning error could waste valuable beam time. But the scientist making the decisions was not standing beside the machine. It was an artificial intelligence system reading detector images, analyzing motor scans, issuing commands, and deciding what to try next. When the equipment behaved differently from the simulation, the AI noticed the error, adjusted its plan, and continued the experiment. Researchers have now demonstrated an AI agent capable of carrying out a real scientific procedure at the Stanford synchrotron radiation light source. It did not merely process data after an experiment or follow a fixed automation script. It observed the instrument, reasoned through intermediate results, and adapted its actions while aligning crystalline samples for X-ray analysis. The experiment raises a larger question. Are AI systems beginning to cross the boundary between helping scientists interpret results and physically participating in the process of discovery? To understand why the demonstration matters, first imagine the machine the AI had to operate. A synchrotron accelerates electrons until they travel close to the speed of light. As magnets bend their path, the electrons release extremely intense radiation, including X-rays. Scientists guide those X-rays toward materials, proteins, batteries, and other samples to study structures far smaller than the eye can see. Facilities like this are enormous, expensive, and heavily oversubscribed. Researchers may wait months for access, then receive only a limited period of beam time. Every hour matters. A failed alignment or poorly chosen scan can consume part of an experiment that cannot easily be repeated. Before scientists can study a single crystal, they must determine how it is positioned relative to the X-ray beam. When X-rays strike the crystal, the regularly arranged atoms scatter them into patterns called Bragg reflections. The positions of those reflections reveal the crystal's geometry. But finding them can be difficult. The instrument used in the study was based on a 6-circle diffractometer. 4 motors controlled the orientation of the sample, while 2 controlled the detector. Moving one angle could help reveal a reflection but push another component toward a mechanical limit. The scientist must combine physical knowledge, detector images, previous scans, and the instrument's restrictions. They may move a motor, record the intensity, inspect the result, and then decide whether to search wider, refine the peak, or try a different reflection. This is not a single calculation. It is an iterative investigation. Traditional automation works well when every step is known in advance. A program can move a motor through a predefined range, collect measurements, and save the data. But real laboratories contain surprises. A sample may be mounted unevenly. A motor may have an offset. A diffraction peak may appear broader or weaker than expected. Background rings may hide the signal. A rigid script cannot always recognize that the situation has changed. The researchers therefore built what they called an agentic AI X-ray scientist. The system used a reasoning-capable large language model connected to a collection of structured tools through the Model Context Protocol, or MCP. Those tools allowed it to read experiment information, inspect detector images, analyze scans, and propose instrument commands. The AI was given the goal and the available operations, but the transitions between individual steps were not fully hard-coded. It had to decide which reflection to search for, how wide a scan should be when a peak was convincing, and what to adjust next. Training directly on a real synchrotron would have been impractical. Beam time is too scarce, and incorrect commands could risk collisions or expose equipment to unsafe configurations. So the team first created a virtual beamline that reproduced essential features of the real instrument. Inside this simulation, the AI could make mistakes without damaging anything. It learned the workflow for locating 2 reference reflections, optimizing their intensity, and calculating the crystal's orientation matrix. An orientation matrix is effectively a translation between the coordinates of the crystal and the coordinates of the instrument. Once it is known, researchers can tell the diffractometer where to move in order to probe specific atomic planes. Without that map, the machine is like a telescope pointed toward an unknown part of the sky. The virtual experiments included realistic complications such as detector noise, inactive pixels, unknown motor offsets, and imperfect sample orientation. The researchers benchmarked different AI models over repeated runs. Most successful runs produced sample alignment errors below 5 degrees, although performance declined in more difficult scenarios and when the system was given less reasoning capacity. Some failures came from imperfectly centering diffraction peaks or handling motor constraints. The results showed promise, but they also demonstrated that the AI was not infallible. The crucial test came when the virtual scientist was transferred to a real beamline at Stanford. For safety, a human researcher remained in the loop. The AI generated the exact terminal command it wanted to execute, and the human relayed that command to the instrument without modifying it. After the machine responded, the AI read the new logs and observations before selecting the next action. This safety relay is important. The system was autonomous in planning and interpretation, but it did not have unrestricted physical control over the facility. The sample was a crystal called cobalt tin sulfide, written as Co3SN2S2. The AI first searched for a reference reflection associated with the crystal's long axis. It calculated the expected motor positions, moved toward them, and captured a detector image. The diffraction peak was present, but it was not where the ideal model predicted. The AI detected an angular offset of approximately 1.22 degrees. The likely cause was an uneven sample holder or imperfect mounting. Instead of continuing as though the theoretical values were correct, the system updated its understanding of the experiment and reused the correction during later steps. That moment is one of the most significant parts of the demonstration. A conventional script might repeatedly return to the original theoretical position or require a human to edit its parameters. The AI treated the unexpected offset as new evidence. It incorporated the observation into its working model of the instrument. After locating the first reflection, it searched for a second one needed to determine the crystal's full orientation. The system selected a suitable candidate, accounted for the earlier correction, and performed additional motor scans to center and strengthen the peak. The detector also contained strong diffraction rings that could have distracted the analysis. The AI remained focused on the relevant Bragg reflection and completed the alignment procedure. Researchers then tested the system on a silicon crystal with extremely sharp peaks and another significant motor offset. It successfully aligned that sample as well. These demonstrations provided proof of concept that the same agentic workflow could operate under different experimental conditions. However, the study does not show an AI independently inventing a research question, designing an entire experiment, and making a scientific discovery without humans. The task was specific: align a crystal. Researchers supplied the physical framework, available tools, safety limits, and high-level instructions. The real-world trials were also limited because synchrotron time is expensive, so the experiment was not repeated enough to establish statistical reliability across every possible condition. The researchers themselves described the results as proof-of-concept evidence rather than a finished autonomous laboratory system. Even with those limits, the transition is important. Many scientific instruments already automate individual operations. Robots can prepare samples, software can optimize parameters, and machine learning models can classify experimental data. But those tools usually perform narrow tasks that were specified beforehand. An agentic system can potentially connect those tasks. It can decide which tool to use, interpret what happened, and revise the sequence based on incomplete or unexpected information. That ability could be especially valuable at synchrotrons, neutron sources, and free electron lasers, where complex instruments generate enormous amounts of data and require specialized experts. An AI assistant might prepare alignment strategies before a researcher's scheduled beam time. It could monitor measurements during the experiment, identify weak signals that deserve closer inspection, and recommend adjustments before an opportunity is lost. It could also preserve operational knowledge. Experienced beamline scientists develop intuition from years of working with particular machines. They recognize strange detector patterns, know which scans are worth extending, and understand how equipment behaves when it is slightly misaligned. Encoding some of that expertise into interactive AI systems could make advanced facilities easier to use, especially for researchers visiting from other fields. But greater autonomy introduces new risks. A language model can misunderstand instructions, overinterpret noisy measurements, or select actions that appear reasonable but are physically unsafe. In ordinary text generation, a mistake may produce an incorrect sentence. On a real scientific instrument, a mistake could waste rare samples, damage equipment, or invalidate an entire experiment. That is why virtual training, explicit safety constraints, and human oversight remain essential. The most realistic future is not a laboratory where humans disappear. It is one where scientists define the questions and safety boundaries while AI agents handle parts of the repetitive experimental search. The system could scan through possible configurations without fatigue, document every decision, and alert researchers when the observations contradict expectations. Human scientists would still need to judge whether the experiment is meaningful, whether the assumptions are justified, and whether the conclusion survives independent testing. The X-ray scientist did not replace that process. It demonstrated a new participant within it. At the beginning of the experiment, the crystal was randomly aligned, and the instrument contained an unexpected offset. The AI had only detector images, motor scans, physical guidance, and a set of tools. It searched for evidence, updated its model, and continued until the sample was aligned. That sequence is still far from independent scientific discovery, but it resembles one of science's most important habits: observe what actually happened, not merely what the theory said should happen, and change the plan accordingly. For the first time at this beamline, part of that reasoning loop belonged to a machine.